This paper was presented at Digital Heritage 2018. Displaying a flat picture in VR cannot provide users with the illusion of being someplace else. Instead, content creators typically capture 360 images. They are far more immersive, while remaining easy to acquire using consumer 360 cameras. However, 360 images cannot provide users with a sense of motion parallax, meaning the idea that, as you move in one direction, objects closer to you should appear to move in the opposite direction faster than objects further away. To solve this, we need some form of 3D information, for example in the shape of a dense depth map. If we have this information, we can easily create a 3D mesh, which will naturally provide a sense of motion parallax as users move around. In this paper, we investigate the extent to which providing a sense of motion parallax from 360 images and depth maps can make users more comfortable in VR. To do so, we demonstrate an interface that allows an operator in VR to easily create a dense depth map from a given 360 image. We also present the results of a user study evaluating user comfort under different viewing conditions and when using depth maps with varying levels of accuracy. To create a dense depth map, we propose using a VR interface in which content creators can use their intuitive understanding of a 360 image to manually model it into a 3D mesh. The operator stretches out a basic 3D sphere into a more complex mesh by placing 3D primitives, such as quads, inside it. To model a more complex object, such as the statue in this image, the operator first needs a segmentation mask, indicating which pixels belong to the object. Using this mask, the operator can then model the object just as easily by approximating it once again with a 3D primitive. Directly from within the interface, content creators can then observe the final results in VR, exactly as it will then be displayed to users. Using this interface, we modeled 4 different scenes for our user study. The ground truth color and depth information for each scene was acquired using a laser scanner. We computed 4 depth maps for each scene: ground truth depth, depth computed manually using segmentation masks for several objects, depth computed manually without segmentation masks, and uniform depth. Users then observed all scenes in a random order. There were 2 user groups. Half of the participants performed the study sitting on a rotating chair, while the other half were encouraged to move around. After a few seconds in each scene, we measured self-assessed comfort expressed orally by the participants on a scale of 1 to 5. 25 users took part in the study. The results show that when users move around in the scene, they do indeed feel significantly more comfortable when there is depth information. This was true both when using ground truth depth and when using the manually created depth maps. However, this tendency reversed when users observed the scene from a rotating chair. This is probably because motion parallax is much less of a factor in this case, giving more importance to the visually uncomfortable stretching artifacts caused by the meshing process. In conclusion, we present in this paper a simple way to provide motion parallax in cinematic VR experiences that use 360 images as input data. We validate the idea that a depth-augmented representation enhances comfort during user movement, and should probably not be used if the experience is only to be viewed from a seated position.